In section 2.2, we're going to be looking at basic differentiation rules and rates of change. Our objectives are to find the derivative of a function using the constant rule, find the derivative of a function using the power rule, find the derivative of a function using the constant multiple rule, using the sum and difference rules. We're also going to find derivatives of the sine function and the cosine function. We're going to use derivatives to find rates of change. I don't have a note card here, just because if I were to have one, the note card would contain what we're about to fill in right here in this space. All right, to get used to some notation, when you look at these 6 problems right here, in front of each of the problems or in front of the brackets, you'll see this little fraction, this notation. It's a lowercase d over dx. This is what we call a derivative operator. It tells us to find the derivative. Much like if you see a plus sign, you know to add. If you see a subtraction sign, you know to subtract, etc. So this is an operation in calculus that tells us, hey, let's find the derivative. Well, lucky for us in this lesson, we don't have to find derivatives using the limit definitions. There are some shortcut rules, and that's what this section is about. So for this first top left example, this is saying, what is the derivative with respect to x of a constant? And if you think of a constant like y equals 5, y equals 5 is a horizontal line. So this is basically asking us, what is the slope, since derivative means slope, what is the slope of a constant or a horizontal line? Well, the derivative of any constant, where c is any number, is 0. All right, this says find the derivative with respect to x of a power function. If I have a base of x with a number exponent, a numerical exponent, instead of going through the limit definition of a derivative, the shortcut is take the numeric exponent, multiply it by the constant that's in front, and in this case it'd be 1. So bring the n, the exponent, in front as a multiplier, keep the base of x, take that exponent and subtract 1. So we do 2 things here. We multiply by the exponent and we subtract 1 from the exponent. So these are our formulas, our differentiation rules, and we'll put them in place here in a minute with some examples. All right, bottom left example, what's the derivative with respect to x of some constant that's being multiplied by a function? This constant is a constant multiplier, it's not just a constant. So there's a difference between the derivative of a function using the constant rule, which is always going to be 0, and the derivative of a function using the constant multiple rule, meaning a multiplier. All right, so right down here, if we're going to find the derivative of a constant times a function, we really kind of put the constant on hold, the constant multiplier on hold. We reach in and we find the derivative of some function. Well, the derivative of some function, that notation would just be f prime of x. We reattach the constant multiplier in front. So our eyes should focus on, our attention should focus on what's the derivative of the function and reattach the constant multiplier. All right, top right here. When we have 2 different functions that we're either adding or subtracting, this is going to relate to terms. Terms are what we add or subtract. We can find the derivative with respect to x of f of x, which would become, the derivative notation would be f prime. And then whether we're adding or subtracting, then we can come over here and find the derivative of g, which would result in g prime of x. So we apply the derivative operator to all different terms. All right, what's the derivative with respect to x of the sine function? Well, that's going to actually result in the cosine function. One might think that the derivative with respect to x of cosine then would go to sine x, and that's partly right. But what it ends up being is the negative sine x. So on one of our upcoming tests, we're going to have to know these differentiation rules and then also respond to some questions on the test about these. So you might want to, if you can, begin to start to memorize these differentiation rules. All right, so let's come here. Example 1. It says find the slope of the graph at the given point. Find the slope. Slope for me as a calculus person means derivative. So I need to find the derivative, and then once I get the derivative, it'll likely have an x in it, that derivative equation. I'm going to plug in the x coordinate of this ordered pair right here. So how do I find this derivative? Well, I don't want to use the limit process. I want to try and use these new shortcut differentiation rules. Well, none of these differentiation rules are matching this equation that I have. This equation doesn't look like any of these forms. So I'm going to have to do a little bit of algebra. So the first thing we're going to have to do is we're going to have to expand 2x plus 3. So maybe off to the side, multiply 2x plus 3 times itself. So once that's completed, then y is equivalent to 4x squared plus 12x plus 9. So this is not the derivative, this is just some algebraic work. Now that I have expanded and multiplied, I'm able to use the sum and difference rule up here to find the derivative of each of these terms. So what we're doing is we're finding the derivative with respect to x, since the equation is in terms of x, of both sides of this equation. So what's the derivative of y with respect to x? Well, we just think of that as dy dx. This is notation that represents the derivative. From a previous lesson, we also knew that alternate notation could be like y prime. You could even put it with parentheses x if you wanted to. If you wanted to change y to f of x, then that could be equal to f prime of x. So this is derivative notation equals, now term by term differentiation, which is the sum and difference rule, the derivative of 4x squared. Well, that term matches the power rule. So we're going to take the exponent of 2, multiply it into 4, that's 8, keep the base of x, subtract 1 from the exponent, so that exponent becomes 1. You can actually think of this as the power rule and the constant multiple rule being combined. So that's just the derivative of the first term. Now using the sum and difference rule right here, we're going to come over to the next term. Plus, well, this understood exponent is 1, so applying the constant multiple rule, 1 times 12, so that's 12, keep the base of x, that exponent gets subtracted by 1, so now we're at 0. Well, x to the 0 or anything to the 0 is 1, so I really don't need x to the 0. I can just simply write 12. All right, let's move on and find the derivative of 9. 9 is a constant, so if I just thought about y equals 9, its slope is 0. This is going to be plus 0. Not that you need to write it, but we'll just at least show it once. Okay, cleaning this up, I'm just going to write y prime equals 8x plus 12. Now, had we gone through the limit definition of a derivative and done all that crazy work, we would have still ended up with 8x plus 12. These are shortcut rules that allows us to get to that derivative a little bit more quickly. Going back and reading the question, I have not found the slope of the graph. All I've done is find the derivative, but that's going to allow me to find the slope of the graph. So now we're going to go ahead and plug in x equals 1. This is x, this is y. Let's plug in 1 since our derivative equation has only x's in it. We don't need the 25. So what's y prime, the slope of y at 1? Plug in 1, 8 times 1, plus 12. So our slope is 20. Y prime of 1 is 20. All right, example 2. You can think of the thetas as x's. Feel free to change the thetas to x's, but that is our variable in this problem. So we want to find the slope of this graph at the point 0, 0. So let's find the derivative and then plug in 0 for theta. All right, so let me do this. If I were to bring in, let me do this. I'm going to rewrite the equation down here to give myself more room. So f of theta equals, leave a little gap, 5 sine theta. Parentheses are not necessary here. It's all understood that theta is the angle, or what we call the argument sometimes, minus theta. Again, you can think of those thetas as x's. If I want to keep theta as my variable, if I want to find the derivative operator would be the derivative with respect to theta. So what I do to one side of an equation, I do to the other. So just think of this as I need to apply that derivative operator to all terms. Terms are what you add and subtract. All right, so what does this notation look like? Well, you can bring up the f of theta, so the derivative of f of theta with respect to theta. Here in a minute, I'm just going to write f prime of theta. That's an alternate way to name this notation. It's shorter. All right, equals. All right, now right here, we want to focus on this term first. What's the derivative of 5 times sine theta? Well, I know sine's derivative is cosine, but I'm also using the constant multiple rule. So I have a 5 constant multiplier in front. This isn't 5 plus, where 5's derivative would be 0. It's 5 times. So the derivative of this term would be the derivative of sine, which is cosine, and reattach the 5. So 5's on hold while you find the derivative of the variable factor of this term. 5 cosine theta is that term. Minus, well, what's the derivative of theta? Well, think of that as just x. If I come over here and want to find the derivative of x with respect to x, the exponent is 1. The coefficient is 1. If I apply the power rule, then I would multiply 1 into 1, get 1, keep the x, subtract 1 from the exponent, and get 0. Well, x to the 0 is 1, so my final answer is 1. So the derivative with respect to theta of theta is similar to this rule, so that's just going to be minus 1. Okay, now I found the derivative, but now let me plug in 0 for my theta. So this is theta, and this is f of theta. So let's plug in 0 for theta. I'm going to change this notation to its also appropriate f prime of theta. So 5 cosine theta minus 1. Now I'm going to plug in 0 for my theta. Well, the cosine of 0 on the unit circle would be 1. 1 times 5 is 5. I still have minus 1. So the slope of the graph, the slope of this graph of the original function at x equals 0 would be 4. All right, we're finding the derivative of the function. So straight up tells us we want to go to the derivative. We don't have to plug in any ordered pair, any point, any x value. We just want to find the derivative. All right, well, studying equation 3, it doesn't look like any of these formulas that we have up here, these rules that we have. So we need to do some algebraic work to get it set up so it looks like something up here so we can use these differentiation rules. So let's do some algebra. When you divide by a monomial, one thing you can do is you can split apart the numerator, putting each term of the numerator over x squared. So I'm going to take x cubed, put it over x squared. Then I have minus 4x squared over x squared. Then I have 3 over x squared. So I'm going to come down here, y equals, I haven't done any calculus, that's why I'm not in the prime. So y equals, let's simplify each of these fractions. So x cubed divided by x squared is just x, minus, in this fraction we can divide out the x squareds. That gives 1 on top and bottom, so we have just minus 4. And in this last fraction, it doesn't look like any of these differentiation rules, but I can bring up x out of the bottom, and in doing so, we adjust the exponent to negative. So 3 over x squared is equivalent to 3x to the negative 2. Now taking a look at this equation, not this prime, because all I've done is algebraic work, so I stay with y. Now I can find the derivative of all the terms. So bring in the derivative operator. I don't bring in dy over dx, I just bring in d over dx. Now when you find the derivative of y, which doesn't match up with x, then that's dy over dx, or simply y prime. The derivative of x with respect to x, well, we just saw that previous, that's 1. Move on to the next term. Derivative of 4 is 0. I won't record anything. I'm now at this final term. This derivative, I'm going to use the power rule. So I multiply negative 2 into 3. So that's minus 6. Keep the base of x. Subtract 1 from -2. That becomes -3. We're finished, done, but just so you know of different forms of this answer. That's the derivative, but there's also some more things that we could do to this. Y prime is equal to 1 minus, notice this negative exponent. I can bring down x cubed to the denominator, leaving 6 on top. 6 exponent is +1, so it doesn't need to move to the denominator. X would go to the denominator, adjusting that exponent to +3. So one form of the derivative answer is here, another form is here, and yet a final term that we should probably look at is, what if we got a common denominator to rewrite this derivative as a single fraction? Well, the common denominator, if I put this over 1, would be x cubed over x cubed here. The common denominator would be x cubed, and I'm just multiplying by a form of 1. So if I wanted to rewrite the derivative as a single fraction, the common denominator would be x cubed, and in the numerator, I would have x cubed minus 6. So any of these three are acceptable. Doesn't matter. I don't know if WebAssign is picky about the format, but if it is, now we have a strategy for getting the correct answer that they want us to insert. All right, 4, we're finding the derivative. Well, notice all these radicals here. We don't have any differentiation rules that involve radicals, just differentiation rules that involve numeric exponents. So let's change the form of each of these two terms so that we can apply the power rule or the constant multiple rule. So keep y, no derivative yet. Square root of x is equivalent to x to the 1/2 power. The exponent is 1 on x, and this understood index or root is 2, so we create a fraction of 1/2. Minus, I've got a 4 times, and this would become x to the 1/3 power. Because again, x's understood exponent is 1, the root is 3, we create a fraction with the exponent and the root of 1/3. Let's bring in our derivative operator. Now, this isn't necessary once you're used to it. I just wanted to point out the notation of the derivative operator. I'm always only bringing in d over dx, never dy over dx. We just end up with dy over dx, the name of our derivative. It's not necessary for you to write it down if you're comfortable leaving it off. All right, so the rate of change of y with respect to x is either dy dx or y prime. This derivative just going to get a little messy because of those fractional exponents. So multiply the 1/2 into the 1 that's in front. So that's 1/2. Keep the base of x. Subtract 1 from the exponent. So 1/2 minus 1 is -1/2. Done finding this derivative. Let's move on to the next term. 1/3 times 4. So we'll have minus 4/3. Keep the base of x. 1/3 minus 1 whole is going to be -2/3 if you got a common denominator. So this is our y prime, or our derivative. We're finished unless we want to report this in a different form. This is a correct answer. Okay, well, what if we didn't want negative exponents? Well, that's an easy fix. Y prime, or dy dx. If I didn't want negative exponents, I would have to drop x to the denominator. 2 is already there. So I'd have 1 over, 2's in the bottom, x to the +1/2. Minus, again over here, I'd keep 4 on top, 3's already in the denominator. X would go to the denominator with a +2/3 exponent. Again, what if I don't want fractional exponents? Well, I could convert these back to radicals, so here's yet another version of this answer. Y prime equals, we're going to have 1 over 2. 1/2 power is the square root, so I just put this x underneath the square root symbol. Minus, I've got the 4, I've got the 3. X to the 2/3, convert it back to a radical. That means x squared, because that's the numerator, or the fractional exponent. X squared, and then this would be cube root. So all three of these forms are correct. It really just depends upon what you're being asked to report the answer in, what kind of form. All right, we're kind of change gears here. This says determine the points, if any, at which the graph of each of these functions has a horizontal tangent line. All right, well, I do know that this graph somewhat looks like a W-shaped graph, maybe something like that. And the visual of this fourth degree function, this polynomial function that has a high exponent of 4, fourth degree, right? The graph looks something like this, and it is going to have some horizontal tangent lines. And it looks like if this equation looks something like that, it would have 3 locations where my slope is 0. So what you're asked to find is the ordered pairs at which these 0 slopes are occurring. So determine the points means I need to find the x and y. When the function has a horizontal tangent line, that means slope equals 0. So coming over here and maybe just kind of creating a little list of what we're doing. Horizontal tangent line means y prime, or the derivative, is 0. Once we get y prime, the derivative, and set it equal to 0, then we're going to solve for x. That'll give us the x coordinate, solve for x. Once we get the x coordinate, then we can plug the x coordinate back into the original equation to get the y. So find the derivative, set it to 0, solve for x, plug that x back into the original equation to get the y coordinate. All right, let's find this derivative. So y prime equals, I'm going to leave off the d over dx. The derivative of x to the fourth is 4x cubed. This derivative, term by term differentiation, we're doing the sum and difference rule. This derivative is minus 4x, and the derivative of 3 is 0. So I want a slope of 0, so I don't plug in 0 for x, because that would get me the slope at x equals 0. I want to set y prime equal to 0. So 0 equals 4x cubed minus 4x. So with this algebraic equation, I can now solve for x, and that will give me half of the point that I need as my answer. So how do we solve this? Well, let's do some factoring. Let's pull out a 4x. So 0 equals 4x, parentheses, x squared minus 1. Check your factoring by always multiplying back in. So either 4x is 0. So now that we have two factors, they're being multiplied, set each factor to 0. So either 4x equals 0, divide by 4. Either x is 0, or set x squared minus 1 equal to 0. You can either factor this difference of two squares, or you can use the square root property. You can add 1. You can bring in the square root. Even roots means you take out the x, but we put absolute value around it, and the square root of 1 is just 1. Once we remove the absolute value here, we're going to get positive negative 1. So it looks like I've got 3 x values where I might have 0 slopes. So I've got x equals 0. I've got x equals positive negative 1. Well, I'm not finished until I get the ordered pairs for each of those. So let's go back to the original equation y. Let's plug in 0 for all the x's. So if x is 0 here and 0 here, we get 3. So that gives us the point 0, 3. This is just function notation for the ordered pair 0, 3. Let's plug in negative 1. So negative 1 to the fourth minus 2 times negative 1 squared plus 3. So y of negative 1, I think that's 2. So the other point is negative 1, 2. And lastly, let's plug in positive 1. So 1 to the fourth minus 2, that's also going to be 2. So the third point where I have a 0 slope is at the ordered pair 1, 2. All right, 6 is the same type of question. Something interesting happens here though. Let's find the derivative and set it to 0. So y prime equals 3x squared, derivative of x is 1. Let the slope be 0. If you subtract the 1 to the other side, you're going to get 3x squared equals -1. Divide by 3. So I'm going to end up with x squared equals -1/3. What's going to happen is when you bring in the square root, we're trying to find the square root of a negative number. There's no solutions for that. You can't find the square root or an even root of a negative number. You can an odd root, but not an even root. So if there are no x's that satisfy this equation, then that informs us that there are no horizontal tangent lines. I think I'll continue this in the next video.